Okay, so today we're looking at rotational motion. So we're taking a problem from the section in the Young and Friedman University physics book on rotational motion. So we're saying power plants, it's been argued, should make use of off-peak hours to store their energy by making something large, a large flywheel rotate. So storing that energy as a rotating flywheel. So in this case, we've got an iron flywheel, and the density of iron is 7,800 kilos per meter cubed, and it's 10 centimeters thick uniform disc. So what we want to find out is what would the diameter of the disc need to be if it was to store 10 megajoules of kinetic energy when rotating or spinning at 90 RPM about an axis perpendicular to the center, and what would be the centripetal acceleration at a point of the rim of the wheel if it was spinning at that rate. So rotational motion. So we're given this is going to be a problem about rotational kinetic energy. So let me just make this image small. It's going to be a problem about rotational kinetic energy. So we have energy stored in a system that's rotating, and it said we needed whatever it was, 10 megajoules or something like that. So the first thing to do is to realize that in rotational kinetic energy, let me see, I have my black pen, that the rotational kinetic energy is given by a half I omega squared. So you might be more familiar with translational kinetic energy, where EK is equal to a half mv squared. When we move into the rotational dynamics, that kinetic energy is given by a half I omega squared. And here our I is the moment of inertia. So that's now going to be our formula for rotational kinetic energy. So what else are we going to need? We're going to need to figure out the rotational kinetic energy, the rotational acceleration or radial acceleration. So we'll write down that. The formula for radial acceleration is just r omega squared. So r is going to be the radius. So let's draw our diagram here. So this is our flywheel. This is the axis it's rotating through. And I'm probably going to make a mess of trying to draw it in sort of a third dimension. And this is the thickness of it here. So this is our wheel basically. This is our radius. And then this is going to be our thickness here. And it's going to rotate at a certain rate and store our energy. So we also have that the density of this wheel, rho, is equal to 7,800 kilograms per meter cubed. So a great place to start off all of these problems is write down all the information you have and draw a diagram before you do anything else. And when I say information you have, that includes things like the density of the iron. It also includes the formula that you're likely to need to know. So if you have the formula, if you have the density, then we might need to work out the volume. So if we're going to work out the thickness of this thing, there's a good chance that maybe we need to work out the volume of the cylinder to get to that thickness. So we know that the mass is equal to rho times v, the density times the volume. So be aware the problem is giving you the density here, so you're going to need it. So try and figure out why you'll need it. Will you need it to calculate the mass? Will you need it to calculate the volume? In this case, we're going to need it to calculate the volume, so that we can isolate the thickness from the radius. I think the radius is given to us in the problem, but we'll go back to that shortly. And another thing we're going to need to figure out is, so our rotational kinetic energy, we said, was given by this formula up here, half I omega squared. So I is something, this moment of inertia is something that we don't have yet. So we're going to probably need the formula for the moment of inertia for a structure like this. So this is basically a solid cylinder, and the moment of inertia, so we'll talk about it, treat it as a disc, say. So the moment of inertia of this disc with the axis of the center at the center is going to be a half m times r squared. So that's the moment of inertia, that our term I from above here. So any other information we have, well, we can isolate. So we know the density. We know that we might need the volume in order to get to the thickness. So the volume is going to be given then by volume is equal to T times pi r squared. So we're treating it as a cylinder. So the volume of a cylinder you might be more familiar with is pi r squared h, where h is the height. Here we're dealing with a cylinder where it's more of a thickness than a height we're interested in. So I think now at that point, this is all the information. Well, let's put the thickness in as well. 0.1 meters. So I think at this point, this is all the information that we have, both, you know, from thinking about the problem in terms of what we know about rotational dynamics, and from what's given to us in the problem. Sorry, we also have omega, which is the angular velocity, is going to be 90 revolutions per minute. So revolutions per minute is no good to us when we try and work through these problems using SI units, so we can quickly convert that, and that gives us 9.425 radians per second, which is our proper units for angular velocity. So now what we could do is, if we have the angular velocity, at this point now we can work out the moment of inertia of our cylinder, of our sort of rotating wheel. So from above, I is equal to a half mr squared, so a half mr squared. So what that tells us then, in terms of we don't have the radius is what we're looking for. So can we figure out the moment of inertia in terms of the kinetic energy and the angular velocity, which we have circled in blue there? We can. So we're going to get rid of this equation here and rewrite the equation that I've circled in blue instead, and work out the moment of inertia from there. So I is equal to 2 times k, or ek times, or divided by omega squared. So when we manipulate that equation on the top right there, we can now solve for I. So that's going to be 2 times the kinetic energy that the wheel is going to have when it's spinning, and that's 10 by 10 to the 6 joules, which is 10 megajoules, which it asked for in the question, divided by the angular velocity squared. So that's 9.425 radians per second squared. And that gives us, we can just solve that now, 2.2, hang on, my calculator's gone, 2.525 by 10 to the 5 kilograms meters squared is the units of moment of inertia. So we've solved for the moment of inertia. Let's put that in blue there, because we're probably going to need it later on. So now we've got the moment of inertia. From that then, we can possibly use, again with circle in blue here, this equation to get to the radius. So the radius is ultimately what we want to solve for in this problem, okay? So now we have the moment of inertia. There's another unknown that we need to figure out before we can sort of rearrange that equation and solve for R. So, as I said, we need the mass, but we don't have it. But we do have some other stuff that will allow us to get to the mass. So we said above here, the mass is equal to the density. Okay, we'll leave it in blue. Mass is equal to density times volume. So the density is given to us in the problem, so we'll leave that as rho for the moment. What's the volume of the cylinder, or the volume of the sphere? We worked that out earlier on. It's going to be T times pi times r squared. So your familiar pi r squared h volume of a cylinder. So now we'll work out what's I. So I, the moment of inertia, is equal to a half m r squared. So now we know we have a term for m here, and it's what I've circled there. So we can substitute that into our moment of inertia. So now we get a half, and when we put that all together, we get rho times pi times t times r to the 4. So we've got an r squared in both of them. So when we put those two together now, we get an r to the 4. So that's our formula now for the mass of for the moment of inertia of the rod, which we know because we worked that out previously. So we worked that out up here. And now we've got a situation where we only have one unknown here now, and that unknown is the radius. So if we manipulate that equation to solve for the radius, capital R here, we get 2i, so just changing things around, 2i over rho times pi times t to the power of a quarter. Stick that into your calculator, and the answer comes out to be 3.68 meters. Now we're asked for the diameter, so remember that's just the radius. So the diameter now is going to be twice that, obviously, which is 7.36 meters. So that if we want a wheel that's 0.1 meters thick or 10 centimeters thick, that can store 10 megajoules of energy when it's rotating and it's made of iron, we've now solved the problem, and we know that we need to construct a wheel that has a diameter of 7.36 meters. Now the second part, we put an extra equation up here, so let's go to, say, red, to solve for the radial acceleration. So now we have the radius and we have omega. So we solve for the radius, and omega was given to us in the question, excuse me. So this is, fairly simple and straightforward here. The radial acceleration is equal to r times omega squared. R was 7.36 meters. Omega was 9.425 radians per second. 9.425 radians per second. And that gives us an acceleration then of a radial acceleration of 327 meters per second squared, which is roughly about 33 Gs. So the acceleration that this wheel, the radial acceleration of this wheel that you construct, is going to be 33 Gs when it's spinning around. So you're going to need to make sure that iron and the construction of it has, enough integrity, enough structural integrity to handle 33 Gs.